Let's get to today's program. Transforming asset health analytics and vibration monitoring in the age of AI. Very timely topics. We've got two experts from Honeywell with us today. Kushagra and Sundaram are going to be leading the presentation. They're from Honeywell. They are the leaders in this APM technology that's unfolding. They've brought some case studies and some use cases that they're going to present in today's information. So, gentlemen from Honeywell, take over the program. It's all yours.
Yeah, let me introduce myself. So I'm Sundaram. I'm working in Honeywell. I'm the director of solution consultant. I've been in this industry for last 25 years, developing and delivering solutions to the various industries, right from power, petrochemical, refining, and been in the multiple disciplines, starting from the engineering, basically the detail engineering, all the way to the simulation modeling and on the AI and the APM recently. Kushagra?
Hi, everyone. I'm Kushagra Thakur. I am a senior product manager on the APM product management team. I'm also a ISO CAD 2 vibration specialist. Been working in this domain for around 15 years. Excited to present this topic to the team here. Okay, so let's get started. Actually, so let's take a step back and look at where we are at today with asset performance management. So, despite years of investment, we are still facing some persistent challenges. The first challenge is around fragmented data and siloed systems. So, we have tools like vibration, oil analysis, and process data. But these all data sources or data sets are all in different disparate systems, which means even the insights are not connected. Secondly, the challenges around limited asset monitoring coverage. So plants monitor only their critical assets like turbines, compressors, while pumps, fans, and motors, which make up the majority, are often ignored. And the third challenge is that we have heavy reliance on experts. So diagnostic tools still require a specialist to interpret data. And that introduces a ton of delay, inconsistencies, and sometimes errors. For sure, like it helps us prevent those issues. And in this curve, if you see, we show the progression from potential failure to functional failure. So oil analysis might detect early warning signs months before the failure. Ultrasound and vibration, if you see, can detect issues weeks before failure. And thermography, noise, and looseness, those show up only when the failure is imminent. So the earlier we detect an issue, the more options we have, such as cheaper interventions, planned downtime, and safer operations. So the challenge is that many plants are still operating too far right on this curve. They only detect when the symptoms are obvious, which leaves little room to act. So our goal is to shift the detection to the left, catching issues earlier across more assets with fewer false alarms. If we move to the next slide. So, one of the biggest blind spots in reliability programs that we are seeing while talking to customers is operational upset. So they are often, deemed as silent killers, which are not visible in vibration data right away, like in the initial stages, basically. But over time, they can cause significant damage. So not all changes show up immediately in the vibration or performance data. For example, a pump may be experiencing a sudden thermal shock or flow surge, and which may look normal in the short term, but in future it can cause significant damage. And repeated or severe upsets also can cause mechanical stress, that can lead to fatigue, distortion, and even hidden cracks that reveal only much later. So while these machines appear healthy, damage is accumulating quietly in the background. Now, let's look at on the right side how such upsets cause damage. So the first one is thermal shock and stress. So, any rapid temperature swings can cause uneven expansion and contraction of metal surfaces. So I'll give you an example here. So in a refinery, say there is a cold water injection into a hot exchanger, and which can create a thermal shock. So cracks can begin to form in tubes or seals, which don't show up in vibration data until much later. The second category here is load swings and pressure surges. Now, sudden changes in load or flow can create hidden stresses on rotating parts. The third is around process excursion. So any short-lived process excursion can also introduce conditions which are outside the design limits. So in a fertilizer plant, say an ammonia slug or water hammer enters a pump, and this creates erosion and deposits inside the casing, and which can lead to rotor imbalance weeks later. And the last line item here is on flow instability and off-design operation. Now, operating far from best efficiency point increases, turbulence, instability, and that's another important factor that we have to consider here. And then, so this is why integrating process data with vibration analytics is so critical. So, process anomalies usually precede vibration signatures. If we rely only on vibration data, we detect it too late. But by combining these two, we can identify these silent killers much earlier and prevent unexpected breakdown. So if we move to the next slide. Now, let's look at this recycle gas compressor trip event in a catalytic cracking unit. So the compressor tripped due to high vibration, and while the vibration alert was picked up, the PF interval, the time between potential failure and functional failure, was too short for maintenance team to respond. So if you look at the frequency spectrum on the right, in clean condition, the BPF or blade pass frequency harmonics are very small and well defined. In a fouled condition, you can clearly see, there is a higher energy at the BPF harmonics. There are strong sidebands around the BPF, which is linked to the shaft speed, and even a shift in the blade pass frequency itself. So this is a clear signature of blade fouling and uneven airflow. So the key takeaway here is that by the time vibration amplitude rises this much, it's already too late to prevent a trip. So the compressor went down for 150 hours, costing $72K in maintenance plus lost production. So the lesson is that vibration in itself is a lagging indicator. We need to integrate that with process and performance data and parameters like temperature, flow to detect early, say, fouling trends in this case before they show up in vibration problem. Now I'll hand it off to Sundaram to talk about how we can properly detect such issues and improve our reliability program.
Yeah, before we get into the solution, how we go about as an engineer in the plant, we really solve this problem, right? So as long as your solutions are well aligned with the fundamentals and the learnings that happened over a period in the plant, then the solution is going to be much more robust. So we always start with a business target, right? So we have a target that could be a maintenance cost reductions or making sure the production is running as planned, or making sure there's no safety incidents are happening, there's no degradation and energy loss happening. There could be different personnel will have a different target in mind, and the first thing they do about is really try to get the data that is relevant to assess where they are in meeting the business target. Right? That's the first step they do. Now we need to get the data. Today, often like we have a silo system. We really need a platform wherein we can get the data from different sources, being it's asset condition data from loop oil system, or from a vibration monitor system, or from a DCS. We should be able to get the data from multiple data sources, and that's what people do by going to the different tools and analyze the trend. Now, first thing you do is more univariate approach, right? You look at your temperature, you look at your pressures, you look at the vibrations, how it is, overall vibration trend looks like, and then decide, do you want to do a detailed analysis? So the first step in doing a trend is normally doing a univariate analysis to understand, is there any statistical change in the trend of the data, right? And that will indicate an issue which I need to further deep dive and understand what could be the problem and what kind of action I need to take. So then I normally go and do a multivariate analysis and try to see basically by combining the different trends. I look at multiple trends and see the correlations, how the correlation has changed, and create a hypothesis, and then go and check in the field what is happening. And then I come up with a assessment on how it is impacting the performance and operation. So because I've taken the data, I've done the analysis, and I have some hypothesis, and I'm checking with the impact of these deviations on the performance and operation. And then I go and look at what is the reliability impact, because these assets are often getting restarted, or basically the downtime is increasing. I can see some of the assets are becoming a bad actor. I need to look at how it is impacting my overall reliability of my production unit, right? And then finally, you create a set of actions to execute in the field, right? So this is what I was doing as an engineer in the field when I was working in some of the refineries. And then what we really need is you need to connect this, and this I do on every situation or on a daily basis on some critical assets, and which is now very difficult to scale because I can hardly look at few assets in a day. What we really need is an automation of this analysis at scale, and with an assist, if it is can be provided, then what I'm doing today is fully automated. All the knowledge what I have is fully should be automated into the system, and systems should start assisting me, right? And I don't believe in doing a black box one model, having a big AI model which is taking all the data and giving a prediction. Rather, I want to replicate all the analysis what I'm doing within the AI platform. Right? So the way the solution was built out is basically going back to the thought process of how the problem is analyzed in the field and actions are taken. The same is replicated at scale in the platform. So we connect to multiple data sources. So whatever the data source, the more the data sources, the more is you're going to accelerate the ROI, because the more the silo you are, you're going to have a limited ROI on the implementation, right? So we should be able to integrate vibration data, the field inspection data, as well as the process data and the controls data. All of these data should be integrated and contextualized first to start the processing in real time. And the next is whatever I do on the univariate trend analysis, I want to be happening in a real time on all the sensor data that is flowing into the system, right? And that is really observing for, is there any shift? What is the trend looks like? Is the average of last week compared to the current value? Is it shifted significantly? Then there is an anomaly started happening, right? So I need to alert the user. So basically, I need to be observing all the available signal in real time and start recording the various anomalies I'm observing it. That may not require immediate action, but I need to start recording all the anomalies that is happening, including, like, for example, if an asset is stopped, I should be able to record an event so that the engineer can come and assign whether it is an unplanned stoppage or is a planned stoppage. If it is unplanned, what is the reason for that unplanned stoppage, right? And what is the cost implication of that? So all that would be possible only when we start recording all the events on the incoming data. Right? And once I analyze the data, then I further want to look at is there any pattern of failure happening? And how do you do that? You'll basically integrate all the data, so including the features that is coming out of vibration analytics. For example, the 1x energy or the 2x and the blade, basically the compressor frequencies, all the relevant important frequencies and the energy associated with that will all be going into this AIML model. In addition to that, we also get the process data that is integrated and assessed as part of this AI model. which is more of a digital twin model, which is predicting what should be the normal behavior for the current operating condition. Right. So once I analyze the failure, I also want to assess how good is the performance or energy efficiency point of view. I want to look at where we are, because sometimes when you're off design, you're operating on an off design state, then that is also going to accumulate some of the stresses on the asset. So the prolonged operation of away from the design points is going to cause later the equipment problem. So, but the challenge here is often the OEM curves are given for a particular reference condition and a reference fluid, which may not be the same what you're operating. So you need to have a first level of normalization. That means it should be independent of your inlet condition. So we do the basically make the OEM curves independent of the inlet condition and try to predict what is the expected and actual, and try to show how far they are off design. Right? And that's one of the often misleaded information today, taking the raw curves and trying to see where you're operating. Right? So that is because your molecular weight could change, your inlet temperature could have changed. So all that matters for this assessment on where you are with respect to the design versus actual. Now, I have done the performance impact, and then next step is I want to look at, based on my AML model, which is predicting how far you are from normal, I want to now see what is the predicted MTBF, right? If you could get a real-time prediction on the MTBF, then that really gives you a way to prioritize which asset I need to focus first, because you know what is the predicted MTBF and what is the consequences associated with each of the asset. If those can be presented in a single pane of glass across a fleet, then that helps me to prioritize which asset I need to focus today and take actions. Right? And finally, all these outcomes should be integrated, and you have to record the events, and then you have to raise basically a case or a ticket, which will be going through the expert analysis and record the findings and what is the remedy action to further improve the reliability. So if this happens in basically the same what I shown here is what is we are automating it, and then you have enough database of this information recorded, which would actually help to build your AI assist module, and that can so assist the engineers. So today the engineer has to do every asset data analysis. Tomorrow, what is the expectation is all this analysis should be automated, and then I should ask questions and get recommendations on what I have to do on the next to improve the reliability of the assets. Right? And all this should be integrated in a single platform, and the data comes in, and you get all the outputs from each of the layers, and it all has to be evaluated in the sequence as I shown. Right? That is also important to get a high fidelity output. Let's go back to the case study what Kushagra was presenting on the process unit. Basically, where it happened is on the hydrotreating unit, where the fouling was often happening, and there was a planned and unplanned shutdown was happening. Right. So we really want to have a solution which will really arrest or minimize the downtime. So as I told you, the first step is doing the streaming analytics that happens on the process and condition. So it looks at the suction temperature, it looks at the ammonia in the inlet stream, and because there is a high chance if there is a increase in ammonia and if there is a decrease in the temperature, this combination is going to lead to the formation of salts in the compressor shaft or blades. So we need to prevent it. In addition, I also look at all my vibration, overall signal and features, looking for some anomaly at the signal level. So that's a first level analysis that happens in real time. So this happens like thousands and 10,000s or 100,000s of data will come in real time when you are going from site to enterprise. And the platform should be able to handle this in real time. Because some of the deviations will not sustain. For example, suction temperature may deviate for a few minutes or even for a few seconds, right? So that also matters. All the fluctuations, abnormal fluctuations should be captured as an event, and which will help in doing the further root cause analysis later, right? When you find a specific failure mode is potential is identified, then you can drill down back and see what are the associated or symptoms, and these could be one of the symptoms that will be raised, right? The second step, as I was telling, so we will have the digitize the performance curve, and we will make it independent of the inlet condition and start looking at what it is the current operating point versus the expected operating point from the OEM curves. And the delta will actually indicate there is a increase in fouling. That could be one of the reason where the performance can also the degrade. So I need to see a trend of this degradation or the deviation. So I will trend the deviation and generate an independent event on the performance deviation. And in the system, so we have configured in the plant, and we're able to get a performance alert on 22nd November, right? So the next is, so we went ahead and deployed the predictive analytics model, which is the performance model is the first principle digital twin model. And the predictive model is more of a data-driven digital twin model, which will be predicting what should be the normal condition or what should be the outlet condition should be, right? And then compare against the actual. So based on that, we can see the onset of early alert at 35 microns, whereas your DCS limit is 75 microns. So you have enough margin or the time to act before it leads to a failure, right? And you also know how much is the energy loss because of the fouling and the performance degradation, because you have an accurate performance model, performance prediction model. So you'll be able to accumulate what is the cost of energy losses in the asset, right? Coupled with the early alert on the from the vibration data, and this particular model is built using the various features from the high frequency data, as well as the overall vibration data, along with the lube oil and seal system. So all the various subsystem data is all integrated, and this model is built, and that's how it is able to predict the blue signal is the predicted value, and the green is the actual. And you can see the onset of the event when it started deviating, right? It is very obvious if it is after some time, it becomes very obvious for the engineer to understand there is a problem happening. But to detect much early is a challenge, right? Because you are going to generate an event at the onset of the deviation. So that's where you need to have a very sensitive, accurate model to really predict this event. The more the number of events, then it becomes a noisy also. So you need to have enough controls so that this event is really not noisy and it's also actionable. Now to make it more actionable, so it first generate a rotor anomaly, and that particular event is basically generated based on your asset strategy. So we look at first the asset strategy, and we have a template built for each of the asset types. And in that, you can see the rules are defined to integrate the output of these three, right? So it looks at the events coming from the streaming analytics. It looks at the events coming from the performance analytics as well as the predictive. So all these events are taken, and the data is taken from these monitoring into the decision system, where you look at the combination of so polytrope efficiency is the residual is becoming higher, right? Which means the expected actual, the deviation becoming higher. So, and then you're also observing there's a radial vibration overall on X and Y are increasing, right? That meaning the deviation from the normality is increasing. And you are also seeing the compressor frequencies and the amplitudes are also increased. So now this is what is leading to a rotor anomaly alert. Before it generates a rotor anomaly alert, I also want to check what is the condition of the lube oil system, because sometimes it might be because of the lack of the lube oil pressure and temperature could be an issue which is leading to this vibration increase. So we need to eliminate it. So you need to have a combination of what triggers. You also need to have a combination of rules to eliminate the possibility of other failure modes, right, or other symptoms which is leading to this failure mode, right? So by doing all of these, now there is a water wash is already in place, but they need to increase the water wash tactical temporarily, and then see the vibration is getting normalized. So then you can see that the rotor anomaly alert is got normalized after the water wash is increased. Now the lesson learned on this one is, if there is a proactive and predictive alerts are generated, then I'll be able to act upon much early, almost like couple of or month earlier than the actual vibration it is leading to, right? And the impact is we're able to reduce or prevent the downtime and the production loss because of those downtime. And you can reduce the maintenance cost because if it is allowed to foul, you know what will happen, right? So you may have to overall, you have to clean it and you have to put back. So you need to have a downtime for it. And by doing this proactive monitoring, you're also avoiding the secondary damage. So which means you are also extending the asset or component life. Right. So that's another benefit you're getting it by acting early on the system. So overall, the outcome is there is a proactive and predictive maintenance practices were established, and there is a collaboration between the process, operation, and maintenance are being established. It's going to take time, but at least it is initiated, and awareness on this application across all three teams were provided, and they started getting familiarized with the system. Right. So the key takeaway is we need to go beyond the point solution if you want to be effective in terms of reducing the cost of lower reliability, right? So and the reliability often being looked from a one dimension, which is basically maintenance, asset condition, vibration. No, reliability, you need to look from a holistic, all three dimension. You need to look at from a operation-driven reliability, process-driven reliability, and make them accountable, right? We need to really make all three people accountable for reliability. It is not just maintenance team, right? By making operations accountable on the various upset, because I'm having a streaming analytics where I'm recording all the abnormality on the various signal, right? And I'm able to identify how many events are related to the process and operation, and I can collaborate with the operations team, right? To prevent going outside of the operating envelope, right? There may be challenges, but getting a visibility to the operation team that this is actually this violation of operating envelope is leading to this particular asset failure or potential asset failure will actually help. If not in immediate action, there will be a awareness and consciousness of how to make sure it's operating all within the operating envelope, right? And maintenance driven reliability, and the more you have a predictive and lesser false positive alerts, the more it becomes realized in the field, and you can defer the maintenance because you can predict the MTBF. If you can predict the MTBF, you can do a better planning. You can also do the deferral of the maintenance, and you can start uh, you can really start with a few assets focused and see how you can really define a strategy to defer the maintenance, right? So that's another aspect that you need to also implement as part of this automation. One of the module is basically define your strategy to defer by looking at the current operating conditions. You may not bring all the asset strategy digitized, but at least most of the key elements that you can digitize actually. Maintenance planning can be optimized because you have a good awareness on what is happening and what is going to happen. Then you could take risk on some of the maintenance tasks, and you can increase the priority of some of the other maintenance tasks. So you can really optimize within the budget that is allocated for the maintenance team. And process driven, like process engineer also it's a key. So who will have to make sure the constraints are being respected. If there is a violation, they need to help out in looking at working with the process control team and the operation team and the operation procedure. Yeah, and in some cases, they may also have to work with OEMs like the compressor manufacturer, or in some cases with the controllers like CCC. They need to look at and make sure that the operations are happening at the design or expected state, right? So all this, there are different savings depending upon the maturity of different customers or a different site within a customer also. It can vary, right? So the operation and maintenance cost reduction can be significant because you have seen that the operation is a silent killer, right? Many people really don't really get much focus over there because and the focus is more reactive in looking at vibration and looking at the impact of the degradation of the mechanical component. So that was given more priority, but you need to look at comprehensively across operation and process, and that can lead to a significant savings. And then you can improve, if you can improve the digitization of your maintenance reliability, then that could significantly also improve your utilization, right? So by having a good, accurate performance model in real time, or in some cases where the composition keep changing, then at least you should be having a, data-driven, like whenever your lab data is collected, at that point you should be able to update and get the deviation and trend those deviation also, right? Even though it is not collected with online sensor, you should still be able to get this trend of the prediction with the daily or monthly data being entered into the system, right? We should get a good visibility of where you're operating, how much is the energy loss, and really required to save the energy in the operations. So by utilizing all these technology and the engineering principle, and so AI is not a black box. AI needs to be a gray box model. So AI model, as much it is becoming a gray box model, the more it will be practical, the more it will be reliable and scalable. And we have experience of deploying this AI/ML models across thousands and thousands of assets, and that's not trivial, right? So deploying model is one, maintaining the model is another, right? If you require a larger maintenance of the effort on the models, then those model is not going to sustain and you cannot scale it. So you need to have a good model. For that, you need to have a good platform which is integrating all the informations. And you should have a good decision rules to drive the action in the field as well as your maintenance strategy.
Fantastic. Sundaram, I think we've got about 8 minutes left for some Q&A here. Are you ready to take some questions?
Yes.
Yep.
All right. Well, I think Well, I really want to talk about the integration into the client's EAM or CMMS system. As you were talking about those alerts being triggered, maybe you could differentiate or help the audience better understand alerts within your Honeywell APM system. And does that auto generate a work order if a PM change, for example, is the result of the analysis and they have to change their preventive maintenance task in the maintenance management system? Talk about how that
Yeah.
works.
Yeah, so we have seen at least when we started the integration with the SAP, so we were actually integrating the events directly to the SAP to convert into a work order. But that's an immature way to really do it because what we found is then the SAP becomes another event management system, right? And work order is cost, right? A dollar is involved in every work order that you are generating it. So you need to have a maintenance request optimizer. So that's another component that was added, wherein you have a define the rules when this particular event happen, and you need to look at your preventive maintenance schedule. So if there is a maintenance scheduled in the next week or next couple of days, then I don't require to act on this particular anomaly that you have detected, right? So you need to have a good definition of strategy to filter out the events and convert into a work order. That is one way. Then the second way is we create a case, and the case goes through a manual inspection or manual analysis of the data and decide this really requires a work order to be generated. And with these two channels, and you can integrate directly to the SAP system or any other CMS system through the messaging layer. So we do have a messaging infrastructure which can be connected to a different CMS system where you are executing your work order.
Understood. I see your colleague is answering a lot of questions directly in the chat, so I'm going to go to a few other ones that we had, Sundaram. And one of them is about the trust in these AI ML models.
Yeah,
The client is new to this. They've heard all the hype about AI. They
yeah,
they they have a book definition of machine learning and how these models continue to learn and improve over time. Is that
yeah.
exclusive, proprietary? Talk about how we build that trust and how those models improve over time.
Yeah. So as I told you, like I myself an engineer in the field, and we have done the various analysis, and then I've been as a software developer, architect, and also consulting different customers to solve different problems. So one of the fundamental thing is the more the engineering knowledge embedded into the different layer within the your AML platform, then that makes it as a gray box model, and that has enough consideration and controls in place. It is so that's where by taking a black box AI ML model, give set of data, let it predict what it when it's going to fail, or let it tell what is the problem that's going to happen. That's often it may solve for a point solution because the data scientist is making it to work. But the moment the data scientist is off and the data itself, like you do a overall of the asset, everything changes. Now again, you have to go and train your model. So it's not a sustainable mode. But if you have put all your fundamental knowledge inside your AML platform, then that has enough knowledge to really discern the data and give you the prediction. Now, here again, there are some tuning efforts are involved, but that's going to be an initial model deployment tuning effort. Recurring effort would be very much reduced. So yeah, again, in conclusion, we really need a gray box model. You need to know what is happening within the AML model, how things are really getting predicted. If you, as long as the engineer can get the confidence, then you can, then they will start believing the events and act on that.
The word that I use is augmentation, right? Like, so you just work alongside these recommender system and help it improve as well. Update your, the failure models that you have, and just it's like you, it's trying to improve your efficiency. So instead of watching over thousands of assets, you have limited set of key assets that you have to look at. So it's basically augmenting you, making you more efficient.
Right. Okay, another big question that often comes up when we're talking about monitoring, condition monitoring from various devices is if the plant already has a wireless condition monitoring system and they've got temperature and they've got vibration through another system, you talk about how you can integrate into those existing systems. And what about, I have a number of plants I've been in where the corporate IT standards about security of that wireless network is sometimes a question that needs to be wrestled with. So let's talk about that, team.
Yeah, maybe I can take that, Sundaram. So we
Yeah.
are working with, enterprise customers like the top five, and, similar scenarios have arisen. And there are two types of scenarios for sure. Like we can, ingest data from different other condition monitoring vendors, but also we have our own, condition monitoring system, Versatilis as well. But the thing is, like from deployment standpoint, also, say one enterprise customer is requesting our solution to be deployed in their environment, and their data is in their data lake. So we have multiple types of integration mechanism as well as deployment mechanism. But the end goal is, just to provide the right set of interfaces that can help solve the problem from vibration standpoint also, right? Like, so all the FFTs or, waterfall and all those different charts which are required to actually do the analysis are also there, so that you don't miss out on the features available at the system one, or other condition monitoring system level.
Right. Okay, team, we have time for one more question, and I want to make sure we get this one in because it comes up all the time. Mark asked, how much background information is needed on an asset before AI analysis becomes effective? We often hear, oh, our data is horrible. I don't know that we can trust that. It might be biased. It might misinform your AI models for training. So how do you solve for that where there's questions about the historical data and how much of that background data is needed before a model can be trained up? Or do you guys already have that from your customer base and you've got a starting point?
So it varies for asset to asset. So in some cases, you may have historical data available. In other cases, you may not have it. So there is always a base model that can be deployed. Like when you look at the multiple layer, you can deploy the streaming analytics, you can deploy your performance monitoring, you can deploy your the false symptom rules. So you can deploy some of those layer, and then over the period, once we get the data, enough data to train, then you start putting into online. So that's we go about in deploying models in a layered manner rather than deploying all the models in one go if you do not have the data.
Right.
Yeah, but it's good to have the actual information about that asset, the physics level information plus, the CMMS information so that it can improve and evolve. So we advise our, customers to for sure do that integration, provide that entire metadata about that asset, provide that metadata about failures in the past so that we can create a good or great model actually that can help them.
Right.
So in
All
the
right.
context of process, we have solved it because we have process simulator. We can simulate with high fidelity the various, we can simulate across various operating regime. We can generate the data. But when it comes to the mechanical conditions, we still rely on the actual data from the field to build the data-driven digital twin models.
That's right. Through the miracle of our digital technology, there is that
Yeah.
simulation that we can synthetically create the data to
Right.
get started. That's fantastic. Well, team, we're out of time for this episode of Reliability Web TV. I want to thank Sundaram and Kushagra from Honeywell for the presentation today.